All right, we're back. We're on page 184. We're still in parametric equations. We've been parameterizing things, which is where you introduce a parameter and then write parametric equations. Parametric equations, I think, are like better in almost every way than non-parametric equations. But we're going to talk about here, which bizarrely is like, if you don't learn them in depth, this is pretty much the only thing you learn about them. You can eliminate the parameter. So it's possible to eliminate the parameter. And what that means is you get rid of it. You write it in just pure rectangular form, x's and y's, no parameter. Why would you want to do this? Well, sometimes you look at parametric equations and you have absolutely no idea what they might be a graph of. And sometimes eliminating the parameter can give you a sense of what you're dealing with, but you lose so much, right? You lose the speed, you lose the orientation, you lose that notion of things happening over time. Basically, you're saying instead of like watching a really exciting race happen, all you want to do is look at the racetrack. And that's what happens when you eliminate the parameters. So let's do it. If I've convinced you that it's a bad idea, let's actually like implement it and see how it goes. So here, e to the t is what x is equal to. So I'd like to write y in terms of that if I can. If I can't, I'll write x in terms of y. Like that's not really an issue. But for this particular problem, I can write this as e to the t and then squared, and then e to the t is x. So this is really just x squared. What is that random line that just showed up there? And can I erase it? What are you? Okay, you're going. So y equals x squared. That's what we've got. But not really, because we have to think about domain and we have to think about range potentially. So for this, if x is equal to e to the t, then I could make a graph and just look at what's happening with x over time, right? And that looks like this. So this is telling me that x is greater than 0, because you can never get to 0, but you can approach 0 if t approaches negative infinity. So yeah, when I eliminate the parameter, I get y equals x squared, but only if x is greater than 0. So if I plot that, it's going to look like open circle here, and then why are you so quick to change? It looks like this. So we eliminate the parameter, we get that. Our domain is x is greater than 0. So like, it's just like worse, right? I know what happened. When I highlighted this, it somehow turned it into a line segment. Mystery sort of solved. I don't know, you probably already knew that. Let's try the next one. So I look at this, and so if you're obsessed with replacing, you want y to be a function of x, this is going to be a little harder. If you're okay with x being a function of y, check it out. Y is equal to t. We have a t here, so we can just say that x is equal to 1 minus y squared. Boom, done. So in terms of graphing this, you might prefer to rearrange it to -1 times y minus 0 squared. And so this is a parabola. And now maybe you want to list all the things about the parabola. Maybe you don't. What else you got? You got your vertex, right? And that's going to be at 1, 0. You have, so we need a focus, we need a directrix. Focus, directrix, we're going to need endpoints of the lattice rectum. We're going to want the focal width, which we actually already know, but let's hold off. Focal width, and then the eccentricity, which I'm definitely going to just say is 1, because for every parabola, the eccentricity is 1. So I know that 1 over 4p is equal to 1, so I know that p must equal 1/4. This is a parabola that's opening to the left because it's a negative y, so it's going to go this way, which means this is your vertex, your focus, your directrix. I find it very useful to have a little sketch here. So the focus is going to be 1/4 to the left. So that's going to be, I guess, 3/4 and then 0. The directrix is going to be 1/4 to the right of the vertex. So that's going to be at x equals 5/4. The endpoints use the focus, so it's 3/4. And then you go 2p in either direction. So I'll say 0 plus or minus 1/2. Focal width is 4p, so the focal width is just 1. And there you go. So not only do we get that, we're able to find everything about it. So this is actually something you should look out for. If you're dealing with conic sections, you might be asked to find everything. And then remember, when you find everything, you can check it. So we haven't really done this yet. So what I'm going to do is start a new document, because why not? I'm going to go to the graph page and do 2 things. I'm going to press menu and 3, and instead of choosing equation, I'm going to choose parametric. I think this is the first time we've done this. So actually, that's not true. I think in the notes about the unit circle, we graph the unit circle using parametrics, but I don't know if I expect you to remember that. So I'm going to type it in what I see here. 1 minus t squared, t. Now here it's asking, like, what are your t values? It always defaults to 0 to 2 pi because it basically is like, let's graph the unit circle. I'm going to change this to like -10 to 10, I guess. I'm just making that up. T-step, not super important. You want it to be small, but there's like a limit. So I'm going to do this, and it's when I press enter, you can see it graph something. If I go back, you can see it changed it to 0.1. I guess 0.1 is the minimum that it would accept for -10 to 10. If I'm going from 0 to 1, it'll accept a smaller t-step. So what's happening is it starts at -10, then it adds the t-step, and it just keeps adding the t-step until it gets to +10. So if I make the t-step be like 5, it's going to go. So it does this thing where it does a better job than it used to. It should just plot -5, -10, -5, 0, 5, and 10, like, and connect those with like a bad line. Oh, it does. Good. Well, I don't know if that's good or not. You can see it like gets worse when the t-step is bigger. So you want a small t-step. The problem is the smaller the t-step, the longer it will take to graph because it needs to deal with more things, and it has like this default built-in minimum that it'll use. So this is the graph of the parametrics. You can totally overlay that with a graph of a parabola. So I'm going to choose this and try to fill it in. So what are you? You're -1, 0, and then 1. And it fits right over it. And then the nice thing is once you've done that, you can use all of these things. So let's find the focus and the directrix, because I feel like for this particular problem, that tells me the most about whether I got it right or not. And so we get the values that we found. So I'm thinking, good job. So I'm going to go back. So you can graph in parametric on your Inspire, which is like a really big deal. We're going to use that a lot coming up. Actually, I think GeoGebra is so much better at graphing that like I tend to shy away from graphing parametrics on the Inspire, but I use the Inspire for a lot of parametric stuff, and we're going to do that soon. All right, here we have a number of choices. So let's say we want to get y is a function of x. So if that's the case, I need to say that x equals 2t plus 1. So x minus 1 over 2 is equal to t. And then y is equal to t, right? So t, but now I know this. So y is equal to x minus 1 over 2, and then minus 2. I'm going to rewrite that in like just a slightly different form. I'm going to pull this out so it looks a little more like point slope. So I can see it goes through 1, -2, and has a slope of 1.5. I think it's better that way. So that's if you wanted y to be a function of x. There's no rule about that. What's nice about that is you know how to deal with it. We could also do x as a function of y. If x is a function of y, then we're going to start off with y equals t minus 2. So t is equal to y plus 2. And now we have this and this. So we're going to say x is equal to 2 times the quantity y plus 2 plus 1. All right, so are they the same? Well, they are the same. It's just one of them, y is a function of x. You know how to deal with it. The other is x is a function of y. That's like way less familiar. So what I'm going to do is I'm just going to solve this, right? So x minus 1 divided by 2 equals y plus 2. So then you could say that y equals 1/2 the quantity x minus 1 minus 2. And if you notice, obviously, this and this are the same. It doesn't matter how you choose to eliminate the parameter, you will get the same thing. There's no restrictions on what t can be, so there's no restrictions on x, so you get the entire line. Did that happen up here? Yeah, you get the entire parabola because there's no restrictions on t, which means y could be anything, so you can go everything here, no restrictions. All right, how about this one? This one, to me, this one looks very much like 14 formulas, right? So they're never far away, 14 formulas, you need them all the time. So here, if x is cosine squared of theta minus sine squared of theta, that I know is one of 3 formulas for cosine of 2 theta. Okay, and then y, 2 sine theta cosine theta, that's definitely sine of 2 theta. Which, like, I was suspecting already, because as soon as I see cosine of 2 theta, I think it's probably gonna be sine of 2 theta, so that it's a circle. So this is a circle with a radius of 1 and a center at the origin. So I know that because I recognize it's basically the unit circle, but going twice as fast, right? The period, because of this, I hate I hate when it double highlights. I hate this, how it like gets darker every time. Like, I know that makes sense, but like, so the period is 2 pi divided by 2, so just pi. So it's a unit circle, but it's not the unit circle. The unit circle takes 2 pi to go around. This only takes pi, so it's going twice as fast. So the equation should be x minus 0 squared, y minus 0 squared equals 1. Or we could do cosine squared of 2 theta plus equals x squared, I guess. And then I got lost in the middle of that. Sine squared of 2 theta equals y squared. Then we'll add, get cosine squared plus sine squared equals x squared plus y squared. So you can eliminate the parameter or you can think it through. Both are like equally good. In some ways, thinking it through might be better because generally it will be faster. But only if you know what to think. And if you don't know what to think, then knowing how to do it is the way to go. One way or another, you gotta get it, right? So this is like a small helping of eliminating the parameter. Also a little conic review. There's actually quite a bit of conics. And domain can change, range can change, all sorts of things can change. But anyway, oh, it says to like graph. I don't want to graph. Graphs are no. Well, I mean, like, you know, this one here, I'll graph it. There, it's a line with a positive slope of 1/2. And it goes through 1, negative 2. And then m equals 1/2. There, that's my like dismissive graph. And then this, there, unit circle. Okay, so we graphed it. We followed the directions. All right, I'm gonna end this here. I will be back in the next video and we will do some more. So I will see you there.